Hey everyone, I'm Paulo Rezec from Federal University of Minas Gerais in Brazil, and we present this work entitled Flocking Segregative Swarm Behaviors using Gibbs Random Fields. In this work, we present a novel stochastic and decentralized approach that allows a swarm of heterogeneous robots to produce simultaneously segregative and flocking behaviors using only local sensing. In this paper, we are motivated to study such behaviors since they are one of the most fundamental mechanisms a swarm must exhibit in order to perform more complex tasks. Essentially, they enable the ability of group formation and cohesive navigation. This behavior has been widely studied in swarm robotics, and the combination allows the execution of several complex tasks, such as area coverage, surveillance, transport, foraging, and so forth. One of the main challenges in developing a strategy that produces multiple swarm behaviors simultaneously consists of combining the interaction among the robots efficiently and robustly. So, to the best of our knowledge, this is the first work to track segregative and flocking behaviors together, starting from a random initial state and using only local information. Recently, two works assuming minimum and local only requirements for segregation of swarm of heterogeneous robots have been proposed. We try to extend the concepts of minimalist relative controller to achieve segregation. The authors demonstrate that robots with only a ternary sensor and controller that maps the sensor readings to the wheel speed can reach segregating state. Also considering local sensing and memory mechanisms supported by communication, Inácio proposed a strategy that combines the concept of particle swarm optimization with the optimal reciprocal collision avoidance to achieve segregation. Following the works that only rely on local information, we assume that our robots only use the neighbor's relative position and velocity to achieve simultaneously segregation and cohesive navigation. However, most of these works only consider collision with other robots. Our method also allows the robots to avoid collision with obstacles in the environment, considering that they are equipped with range sensors such as infrared sensors. One of the earliest and most influential approaches to steer a swarm of homogeneous robots using only local interactions was proposed by Reynolds. While most works on this subject deal with homogeneous groups, some use heterogeneous robots to study the flocking of distinct groups. Moment extended the flocking mechanisms with status-specific attraction rules to model different attraction forces between two groups of robots, producing a mixed species flocking. Ducatelli proposed a mechanism that emerged cooperative self-organized behaviors to solve complex tasks using simple local iteration between the robots of two different groups. Some works tackle the problem of segregated navigation, in which the robots start in a segregated state and have to maintain the segregation during the navigation. For example, CentOS introduced a novel concept called virtual group velocity obstacles that combine the concepts of flocking and velocity obstacles with abstraction to represent the groups. To improve performance of such approach, Inácio proposed the combination of optimal reciprocal collision avoidance algorithm with the concepts of flocking. Different from these works, our approach simultaneously generates segregation and flocking behaviors. The robots start in a complete random state, and as they move around, they segregate into different groups and keep the segregation while navigating. The general idea of our methodology consists of modeling the configuration of the swarm of heterogeneous robots as a Gibbs random field, and then sampling velocity for each robot in a decentralized way, which leads the entire swarm to converge towards the global minimum of potential. In the paper, we show how we extend the Gibbs distribution to a decentralized probability function that computes the probability of a robot reach a velocity given only the neighborhood information. The use of appropriate potential functions allow us to reach flocking segregative behavior. Here we propose combining the Coulomb-Buckingham potential with the kinetic energy. The Coulomb-Buckingham potential is a combination of Lennard-Jones potential with Coulomb potential, used to describe the interaction among particles considering their charges. In this paper, we took advantage of such mechanism to model the swarm heterogeneity by setting the particle charges. In short, the Coulomb-Buchner potential defines the attraction and repulsion among the robots. We assume classical mechanics to compute the kinetic energy produced by relative velocities of the robot's neighbors. The kinetic energy represents the relative velocity of the neighbors and allows the velocity consensus among the group. Finally, given the probability function and the potential energy, we use Metropoulos-Hastings algorithm for sampling velocity for each robot in a decentralized way. To evaluate the performance of our approach, we conduct a series of simulated experiments. We first analyze the segregative behavior by measuring the method's performance for different configurations and compare the results with other methods from literature. Then, to analyze the flocking capabilities, we evaluate the velocity consensus and the cohesion among the robots when there is noise in the sensor. Finally, we perform experiments with real robots as proof of concept to show the feasibility of our approach in real scenarios. We consider the work proposed by Santos as a baseline since it assumed global knowledge about the position of the robots leading to a fast convergence rate. To evaluate the segregative behavior, consider only local information. You compare the convergence rate of our approach against the one presented by Mitrano and Inácio. We also contrast our methodology with a deterministic gradient descent approach using potential differentials to show that such mechanism may be easily trapped at local minima. By analyzing the segregation using the number of former clusters, we can see that our approach executes relatively well for a small number of groups, even for increasing number of robots per group. The exception is the gradient descent method, which gets trapped in local minima and cannot reach the segregated state. Regarding the performance in terms of number of iterations to reach segregation, you can see that methods have similar performance on average when increasing the number of robots. However, all of them are significantly slower than the baseline, which uses global information. When the number of groups increases, our approach significantly outperforms the others, with a performance close to the baseline, which uses global information. When there is a large number of groups, robots usually get trapped by other groups and cannot reach segregated state. By relying on the stochastic nature of Gibbs Random Field, our approach can handle this situation better. When we vary the number of groups, we can see that Inácio have a better performance. However, the method proposed by Inácio does not reach the minimum number of clusters on several occasions. So, it may be converging faster, but to a suboptimal configuration. On the other hand, our method may take longer due to its stochastic nature, but has much better success rate. To evaluate the effectiveness of our approach in producing flocking behavior, we carry out some experiments. We analyze them regarding the average distance, cohesion, and consensus speed between the robots of the same type. The robustness of our method is assessed by adding Gaussian noise to the sensor model, so the relative position and velocity estimate are not reliable. As expected, increasing noise in the sensor model significantly impacts the velocity consensus. We observed that up to 6% of noise, the swarm is able to maintain the flocking segregative behavior for the experiment's configuration. When we apply 10% of noise, we notice the velocity consensus degrading and consequently the flocking behavior does not converge. However, even with the noise, we can segregate the swarm to the minimum number of clusters most of the time for a sufficiently large number of iterations. To evaluate the feasibility of our approach in real environments, we perform proof-of-concept experiments using 5 epoch robots. The robots receive velocity commands from a remote computer executing ROS. Given that our robots do not have any sensor that allow them to estimate the relative position and velocity of neighboring robots, we emulate such sensor using OptiTrack motion capture system. Here we consider a bound environment as a square area of 2 by 2 meters restricted by walls. We set the sensing distance to 0.3 meters, and as we have only a few robots, we evaluate cases with 1 or 2 groups. The video shows the performance of our approach using real robots. As you can see, even with the noise in the velocity consensus, Due to the uncertainties observed in the real settings, the robots can read segregation and also keep the flocking behavior. This paper presents a novel decentralized approach that allows a swarm of heterogeneous robots to achieve simultaneously segregation and flocking behavior using only local sensing. Results show that our methodology could segregate a group of heterogeneous robots while keep cohesive navigation around the environment. In future work, we intend to build a new robot swarm that is equipped with distance and bearing sensor and temporarily combine their information to locally estimate their relative velocity and position. Moreover, there are several opportunities for future studies and application using the Gibbs Random Field framework. In particular, I intend to investigate the possibility of performing more complex tasks, such as shape formation and transportation. So, thank you for watching this presentation, and for more information, please visit our GitHub page.